Chapter 13, number 54. A 3.55 gram bullet embeds itself in a 1.47 kilogram block, which is attached to a spring force constant 825 newtons per meter. If the maximum compression of the spring is 5.88 centimeters, A, find the initial speed of the bullet, and B, the time for the bullet block system to come to rest. So we should draw our situation. So what we have is a bullet traveling with some speed v0, hitting a block that's at rest, and then they collide inelastically and the bullet gets stuck inside. We assume this happens very, very quickly so that the block has not really had a chance to move very much before the bullet has come to rest inside of it, but that gives them together some forward velocity v1 because the momentum has to be conserved, and then the block moves against the spring until it gets to some distance a, at which point it's at rest, and then it will snap back and go back and forth forever. During this process, there is no conservation of momentum because the spring is doing work on the block, but there is conservation of energy because spring forces are conserved. So what we really have going on here is between here and here we conserve momentum, and between here and here we conserve energy. We cannot conserve energy in the first bit because this is a non-elastic collision and we know that some kinetic energy gets lost. So let's do that first bit. Let's take our momentum and say that our original mass guy m1 times v0 equals the final mass, which is m1 plus m2 times v1. And therefore v0 is going to be the sum of the masses over the bullet's mass all times v1. The sadness there, of course, is we don't know v1. So we're going to get v1 by using the energy conservation. We're going to say that the energy at the start, which is 1/2 the sum of the masses times v1 squared, is equal to the energy at the end, which is only potential because the masses have stopped moving. So it's just a half Ka squared. So we can find that v1 squared is K over m1 plus m2 times a squared. And I suppose we could get that number. So we say that v1 is square root of the spring constant. Well, our spring constant is this. And so its value is 825 newtons per meter. And we'll divide by the masses. And the masses we have are m1 and m2. You gotta be very careful that they change units on us, which is kind of annoying. So it's 3.55 grams divided by 1,000, and we'd have kilograms. And then here we'd have 1.47 kilograms. And so all of that goes there. And then times A. And A is this, this distance. So 5.88 centimeters divided by 100 turned into meters. And we end up with 1.391 meters per second. And based on our 3 sig figs, we really get that v1 is 1.39 meters per second. Sadly, they didn't want v1, they wanted v0, so I have to go back up to here and get v0. So v0 is the ratio of masses, so it's going to be 3.55 over 1,000 plus 1.47 kilograms over m1, which is 3.55 over 1,000 kilograms, all times this speed, 1.39 meters per second, and we get 576.96 meters per second, which clearly becomes 577 meters per second, which is pretty fast. It's fast in the speed of sound, for instance, but not unusual for a bullet, which often goes fast in the speed of sound. That's why you get that crack when it fires. So that's part A. And part B, we're going to have to apply somewhat differently, so let me clean up and do that. For part B, what we want to do is notice that what we have is the thing that goes over to A, back to here, over to minus A, and back. That's one period, and we want 1/4 period. So our time is 1/4 of the total period, and we know the total period is 2 pi square root m over k. That's that period mass relationship we keep coming up with. So this will be pi over 2 times the square root of, which mass? Well, we really want this mass will be m1 plus m2, so 3.55 kilograms. Right, 3.55 over 1,000 kilograms plus 1.47 kilograms, all divided by 825 newtons per meter. And when we throw that into a calculator, what we end up with is 0.066385 seconds, which becomes 0.0664 seconds, or about 6/100 of a second.